Good evening, ladies and gentlemen. Welcome to the first of what I hope will be an enjoyable series of the Master's lectures, although the Master, you'll be pleased to know, will not be one of those giving them. We're delighted this evening to have as our inaugural lecturer for this series, Tim Leighton, Professor at Southampton, and he's just told me now Emeritus Professor at Southampton. This makes me feel like the ancient of days because I'd already been a fellow for a few years when he joined the college as a research fellow in the 1980s. We were both, of course, much younger then. The infuriating thing is that he hasn't changed a bit in the intervening nearly 40 years. I can't say the same for myself, or indeed for many of the others who were around then. Tim is a fellow of the Royal Society, and he's the world's expert on bubble acoustics. And is going to, for those of you who are not scientists, by the way, this has nothing to do with bubble tea, nor is it about the South Sea bubble, which was one of the very few bad investments that the college didn't manage to put any money into. But he's going to talk about the impact of bubble acoustics on climate change, dolphins, spaceships, the antibiotic apocalypse, and just about everything else. Tim, welcome back to Magdalene.
Thank you very much, Master, for that introduction, and thank you, College, for inviting me. Oh, good, thank you. All right, the next test is, can you hear this sound? Yep. This sound. Okay, that's the noise of a dripping tap. Normally people look frightened that their lecture theatre's leaking, but it's not the case. That's the noise of a dripping tap, and we're very familiar with that, and we're also very familiar with what a dripping tap looks like. And I'm demonstrating that here with this drop of milk that's falling into a black cup of coffee. And I'll play it now. So the milk drop falls, it produces this crown effect and a crater below. And as this crater rebounds and closes up, pretty much the same liquid comes out as went in, the milk. So if you want to be a cool scientist at parties or high table or something, when someone asks you how you want your coffee, you can say white, and as that drop comes out, you can catch it and say black. Right, but nothing that you've seen has much to do with the dripping sound that you heard. And I can prove that here with this picture of a drop of water falling through air into water. And in the water, I have an underwater microphone, which we call a hydrophone. Hydrophone is a word I'll use a few times this study. And as the video plays, the signal from this underwater microphone is shown on the left here. And to keep in synchrony with the video, a little line will track across it to show where we are in the time that's, for the picture shown here. And this is the plink here. So I'll give you a countdown as we approach the plink, so you'll be able to see what it is in this video that causes the plink. So here we go. The drop hits, no plink. Crater opens, still no plink. Crater's opening, crater's closing. Watch the bottom of the crater in 3, 2, 1, blink. So that plink comes from that tiny little bubble, because bubbles are the most powerful, naturally occurring sound sources underwater. So there's the bubble. And every time you hear a plink, you know a plink followed by a silence increases the bubble count in the world by 1. And also you know the size of that bubble, because they're like underwater bells. A small bubble gives out a high note, blink, and a big bubble gives out a low note, blonk. So if you hear blink, blink, blonk, blink, you know 2 small bubbles, a big bubble, and then a small bubble. And that's important, for example, to do with this. This is a methane seep in the ocean. It's in the seabed. And in the seabed, there's a lot of stuff like this. And its common name is called fire ice because it burns in air. If you take methane, which is a gas that comes out the back of cows, you dissolve it in seawater, and you keep it under you keep it cold, and under the kind of pressures you get in the oceans, it forms this sea ice, and it's locked away there. And it's really good that it's locked away there and not in the atmosphere, because 1 molecule of methane gas is 20 times more powerful in terms of causing a greenhouse effect than 1 molecule of carbon dioxide. And there's a lot of it safely locked away in the seabed. Globally, there's twice as much carbon locked away in methane hydrate as there is in all known conventional fossil fuels. So there's a huge amount of it, which brings us to the first apocalypse. This is an extra one to the ones in the title. So it's an apocalypse scenario. So the greenhouse effect occurs, the oceans warm on average, this is very simplified. This methane hydrate gets warmer and dissociates into methane gas, which rises up through the ocean and enters the atmosphere, where it causes increased greenhouse effect, increased warming, making the oceans warmer, making more methane bubble up in an apocalyptic scenario. Now, it's actually very complicated. There's a lot of microbiology, there's other chemistry involved, and the extent to which this will happen is currently quite hotly contested, but it's nevertheless important to take measurements of what's happening here. So we would listen to it and you think, okay, I'll listen for those plinks and silences, at least I'll be able to count how much methane is bubbling up from the seabed. But it's hard because you see how many bubbles there are. You're not going to hear the silences because they overlap. So you've got overlapping plinks like this. So how do we deal with that? Well, I published a paper. I'm going to show you a number of papers, and it's instead of an acknowledgement. So it's got the co-authors on. And again, if anybody wants to look it up afterwards, this is the paper. Quantification of undersea gas leaks from methane seeps by the acoustic emissions. And what this says, it says, look, if these plinks overlap, there's a bunch of equations that will tell you how it works. So we're going to go through these equations. Now, there's no need. You've already got them in your head. You already know them. And I'm going to prove that to you now. I don't have to teach you those. What can we do with these equations? We can do what's called a prediction. You know what a prediction is. A prediction means we take some kind of physics sausage machine, and we take a description of the world, methane hydrate, greenhouse gas, the atmosphere. We take all that physics that we know, description of the world, we plug it into these equations, and they will predict the sound. And computers are really quite good at that. But that isn't the problem I set. The problem I set was listen to the sound and tell me how much methane is being released. And for that, you need to do an inversion. You need to run the sausage machine backwards. You take the sound and you run all the equations backwards, and it tells you a description of the world, what's happened. Computers find this quite hard. Humans are fantastic at it because we've got all these equations in our head. Here, I'll prove it. Here is a sound from a hydrophone, and I'm going to play it, and you can tell me there were many, many little bubbles, and just before the end there was one big bubble. Here we go. Hear it, the big bubble at the end? Humans are great at that. Fine. So so we put that. We've got sensors like this on the seabed. We use it for other things. This is an example in the North Sea of a carbon capture and storage reservoir, whereas to offset all the carbon that's going to the atmosphere as a result of fossil fuel burning, that carbon is captured and shoved down into depleted oil reservoirs in the seabed. And obviously we've put sensors up on the North Sea seabed to ensure the integrity of these, make sure there's nothing leaking out from it. So that's loads of fun. But once you've got these equations, you don't have to stay on Earth. So here we go. This is Titan, Saturn's largest moon. And we can start doing all sorts with that, knowing these equations. This is a picture of Titan. It's quite beautiful. You see this purple haze around its rim? That's a thick atmosphere like ours. It's very like ours. It's mostly nitrogen, few cyanides and smoggy things. And it's there because Titan is 890 million miles from the sun. So it's very, very cold. If it had been in orbit around Earth, there'd be no atmosphere like this because this moon gets quite hot in places and the atmosphere would have boiled off. But out there, 890 million miles away, it's a lovely thick atmosphere. And in the late 90s, we were all looking at it and taking spectrographic information of what chemicals were there. And this led to a fantastic conundrum because some of us thought that with the chemicals there, we would have waterfalls on this world and streams and lakes. Not made of water, because the water is ice, but made of that same gas, methane and ethane, which at these temperatures turn to liquids. So you've got gases, you've got seas, lakes, oceans, possibly. And no one could tell because no one can see through this thick, smoggy atmosphere. So a 7-year journey started on this huge NASA rocket, Cassini. And on the side of it, the European Space Agency placed this rather large, well, a wok this big, effectively. That's Huygens. And Huygens had a whole suite of instruments on it, but the idea was that Huygens would parachute through the atmosphere and land on Titan's surface, and we'd discover what Titan was like underneath this cloud of smog that we couldn't see. Now, as the date came closer, we were getting very nervous because 3 really important spacecraft, the Beagle 2, Mars Polar Lander, Mars Climate Orbiter, had all failed. That either systems had broken down or they're smashed into Mars unexpectedly. And we were wondering, oh no, what would happen if after a 7-year voyage the same thing happened to Huygens? And I'd said, look, if it does happen, and the last thing we hear on its microphone is a splash and not a crunch, mission over, we've solved it. There is a lake somewhere else other than Mars, other than Earth, sorry. But that presupposes that we would recognize it as such, because the human brain calibrated on Earth would running the inverse problem backwards would say, yes, although I've been calibrated on Earth, I can recognize that as a splashdown on Titan, 108 degrees below zero in a lake of liquid ethane and methane. Now, until we've got those measurements, we can't test the ability of the human brain, except we can use a computer, feed it in the description of Titan, and run it forwards to predict a sound. So I did that, and as we were just days away from Huygens parachuting, the BBC produced an animation of what they thought a splashdown was like, and we attached my prediction to it, and then you'll be able to see what the splashdown calculation sounded like. So here is the BBC video, and as you watch Huygens come down, listen for the splashdown. The human brain's pretty good. It's a splashdown. Now, as it happened, Huygens landed looking at this. It's a camera, and it's just pointing in one direction over a snowy, muddy field. If there'd been a waterfall behind it, this camera would have never known. But a microphone might have heard it, presupposing that your brains can run the inversion on Titan for a waterfall. So I calculate the sound of a waterfall on Titan. It's recognizable, such. The nice thing is later tests showed that this was probably a dried out lake bed. And in fact, later extreme flybys showed a lake on the polar regions made of liquid ethane and methane, and you can probably see these little streams and rivers and things. So it's out there. And one day, there'll be another mission. I might not be around anymore. And we'll be able to test my theories. And you'll see this as a theme in my work. Do something no one can ever prove till at least I've gone. So I've got decades of dinners and talking out and dinner parties out on this and never being disproved. And it's only, it'll be a long time till I'm disproved. So, but I was advocating for use of microphones in spacecraft because NASA's business model, when it talks about missions, it talks about life. We'll find the molecules of life. We'll find life. And then they never do. So they say, but look at the pictures. Look at the pictures. The pictures are great. Forget about the promises. And that's the business model. And I was trying to say, let's bring microphones. We've never heard another planet, really. So I started publishing Sound of Titan. I published the sounds of all sorts of things, saying, look, we could design equipment for these missions to measure lightning on Venus, dust devils on Mars, ice volcanoes on Saturn's moons, Enceladus. Didn't really get any traction. but I was quite passionate that we get microphone missions on space probes. So I changed tactic and asked a different question. Strategy. What would our voices sound on another planet? And so you take the equations of how the voice is generated and developed a voice changer, which I gave out free to planetaria around the world. And it's very successful. But the most interesting use of it was a pop star from over in Europe. And she sang a song about Venus, and halfway through she turned on the voice changer so that her voice became what her voice would be if she was standing on Venus and could sing and survive. So here we go, I'll play you that clip.
Lottie, die heeft 2 regels ingezongen. Ja. En die opgestuurd naar de University of Southampton in Engeland. En daar heeft professor Leighton haar stem vervenust.
Oké, nou maestro, geef me maar muziek. Oh ja.
Ja, dat ligt er al.
Liedje over Venus, hè, natuurlijk.
Ja, natuurlijk.
God is on a mountain top, burning like a silver flame. God is a beauty and love, and Venus was her name.
Ja.
Now, though she's making a face like that, she's actually not lowered the pitch. She's not trying, but she knows what it's going to sound like, so she's altering her face. She can't help herself. There's no time in this lecture to explain why that happens, but if anyone wants to catch me after, or in the questions, I'm very happy to explain how that phenomena occurs, and why Venus is the best place for sounds. Right, let's move on. Okay, now we did, after all this pressing by me and the co-authors of this paper, we did finally get an incredibly successful microphone mission to another world. So in 18th of February 2021, the Perseverance rover landed on Mars. Here's Perseverance, and it had a friendly little helicopter Ingenuity with it, and this was wonderful. Mars is shaped by the sun and the wind only. It's not like this planet. There's no geotectonics. There's no running water. It is just the sun and the wind. And why that occurs is because go to the equator on a hot day and there's a 30 Celsius difference between your feet and your waist. There's a huge temperature gradient which overnight can invert and change the other way around. And this drives really strong winds in the thin atmosphere. So here are dust devils, for example, on Mars. Dust devils on Mars can reach 5 miles high and be so big they generate their own lightning, we think. So it's an extraordinary place, even though the atmosphere is thin. So the idea is, how do we investigate this? Well, you might think Perseverance would go out there, set up a rig, a frame about 10 meters wide, 2 or 3 meters tall, fill it with thermometers and anemometers to measure the wind, and take all the data, and that would never happen. And it never happened because space probe missions are limited by battery, weight, ruggedness, and what we call bandwidth. That means how much data is in the signal. You know, a television signal has far more bandwidth than a telephone signal because it's got the video as well as the audio. And this experiment with a rack would be too heavy, too much power, too much bandwidth, and not very rugged. So we decided we'd do the whole thing with a microphone. And this is the plan. Perseverance had a laser, not really for acoustic use, for geology, but we kind of co-opted it for a bit and fired a laser out, and the laser hit a rock 10 meters away. And the rock exploded and sent out sound waves. And I'm going to concentrate on these little black elements of the sound waves, the ripples going out. These are the wavefronts. So as these go out, travel out from the sound, I'm going to tell you that if you draw a rays at a right angle to each of these wavefronts, you get the path it travels. I'm following these because they're heading towards Perseverance. Now, it's fast. The sound speed is high near the ground where the atmosphere is warm, and the sound speed is slow higher up where the atmosphere is cold. So look at these wavefronts. So what we used to call multimedia when I was a lecturer. So it's slow and fast here. So as they propagate, it's not going to propagate like this. It's going to actually start turning up because this is moving faster than this, like the way a tank turns. Right, so As it propagates, these wavefronts move up, and then they hit the microphone on Perseverance, like that, with those rays. And if Perseverance was to follow the line of sight of the ray arrival, it would arrive at a different point from the area it blew up. So there's a difference. Now that isn't really, that's not really the sum total of what we looked at. We looked at all sorts of other things in the sound signal, but it gives you an idea of what you can do with sound. And we looked at the turbulence from the sound, so we got a heck of a lot out from just some cracks. And even we flew Ingenuity about 100 meters away. Couldn't come any closer for fear of collision, because you can't pilot it because there's such a long time delay. So you've got to have an AI filling in the gaps. So we could hear the rotor sounds from the Ingenuity 100 meters away. And we also use that to get quite a broad spectrum from, I think it's about 400 hertz, the lowest of the rotor frequencies, up to 30 kilohertz. And that told us lots what you need to know about the atmosphere on Mars. So, anyway, back to Earth. Earth, if we want to look at bubbles, there are more bubbles in the ocean than anywhere else. This is a photograph I took, half above the water, half below, and you can see these clouds of bubbles underneath the ocean as waves break. And we're going to look at the kind of use that we talked about before, where plink silence increases the bubble count by 1, this sort of sound we heard earlier. Right. And this is important because about 1,000 million tons of atmospheric carbon dissolve into the ocean and perhaps come out of it in stormy circumstances, something like that. And that has a big effect on climate models, but the word about does a lot of heavy lifting because we don't really know how much. We don't know the parameters. So I set about looking see whether we could find them. And obviously, if a wave breaks and we want to know how much carbon dioxide is dissolved into the ocean, we need 2 counts. One is the number of bubbles and their size when the wave breaks, and the other is sometime later, because the difference will be gas dissolving, put very simply. Now we know that as a wave breaks and traps air, we'll trap some atmosphere, and they'll ring like little bells. So we get our first count quite easily. The problem is the second count. Here's the first count. They make little sound. That's before dissolving. Then big bubbles rise under buoyancy. Small bubbles are pushed down by turbulence and circulation, and dissolution happens. And also what we call exsolution, where gas comes out of being dissolved into the bubbles. And you can't count after dissolving because they're silent. You can't listen to them. They're in the silent phase. But they are still bells. Now, if I was to handcuff and blindfold you, all of you, and take you into a room and say, maybe lying or not, but this room has bells hanging from the ceiling you're not allowed to touch, you might shout at them and see if they hum back at you. If you've got a piano and you press the sustaining pedal and shout at the piano, it'll hum back at you. Same for a guitar, through a resonance effect. So we thought, fine, well, we can send sonar pings into the ocean, and our brains, if our brains can do the inverse problem and tell that there are bubbles there, then we train the computers too. So I'm going to play you some sonar pings firstly without bubbles there, and then with some bubbles. This is the experiment. Get a couple of my PhD students, drop a microphone in the water. They're standing on some bit of scaffolding here, and then we play these sonar pings. Right, so this is first without and then with bubbles. These are sonar pings in bubble-free water. And now the same pings after a wave has passed and generated bubbles. So there's a lot of reverberation there, and we can use that kind of thing to tell us how many bubbles are there. So that was great. We did that a lot. That enabled us to build models of the ocean. So this is a model of the ocean measuring about 100 meters by 100 meters in the horizontal, going to a depth of about 15 meters. And all these blue things are bubbles generated by breaking waves in our model. And the blue bubbles are small, they're 25 microns radius, and the big bubbles, which you'll probably see floating near the top, near the end, because buoyancy is stronger for big bubbles, they're about 250 microns radius. And we run this We can log all the bubbles being generated, and we can log where every molecule of carbon dioxide goes. And here we go, here they run. And you see the bubbles being pushed down by circulation and turbulence. And you'll see perhaps them starting to form lovely Y shapes, which happens through a process called Langmuir circulation, which is a big circulation in the ocean, 10 meters or more radius, caused by the wind blowing over the ocean. And you can see you have got the reds near the top. So here we've logged now where all the carbon dioxide goes. We've ground truthed this model against the experimental measurements we make, bish bash bosh, and we've found out the parameters we need, which again we published. Nice paper, asymmetric transfer of carbon dioxide across a broken sea surface. I don't want to leave you there. I want to show you the experiment. Here it is.
Watch out! Bloody hell.
Oh, I find it so hard to recruit and replace. Now, the masters of underwater sound are these things, humpback whales. And they're doing a behavior here that we call bubble netting. And what they do is one whale swims down deep, one more whales, swims around and releases bubbles from its blowhole, which is formed from its nostrils gone to the top of its head. So it blows this, and then trapped inside this net a bunch of fish, and the whales then come up from below with their mouths open and eat them all because the fish don't leave the net. Here's a video. Great story. It's been known about for about 100 years, but I saw this and a question, but why don't the fish leave the net? It's just bubbles. We know salmon jump up waterfalls. Bubbles aren't afraid. So I thought the story isn't really about these two whales. It's about this one here. It's barely visible. Because I thought, it's not these two, it's this one here. So what's happening? Well, I thought, look, this is a quarter of the net with bubbles in. Multimedia again. So the whale is going to send out wavefronts of sound like this, and when they get trapped in the net, it gets slowed down. So the wavefront turns into the net. But then, as it hammers out through the top of the net, it's now the other way around. It's slow within the net, and this has now gone inside the net, and it's fast, and it's going to come back. And so it's going to act as a waveguide like that, trapping these bubbles in this net. Here, I'm going to play the call that the whales only make when they do this, and I'll show you an animation of the ripples happening. So it does something like that and makes a wall of sound. So a fish within the net not only feels subjectively quite a loud, frightening environment if it tries to leave the net, but these frequencies are high enough to resonate swim bladders. And if you're beyond a certain age, you'll know that resonance of your bladder is quite an uncomfortable vibration to live with. So there's a lot of effort in these high frequencies. The whale is doing it for a purpose. So the high frequencies are right at the top of a whale's range, and I think it's doing it because lower frequencies would not resonate with the swim bladder, and they would actually leak out the net. They wouldn't be trapped in this way. So coded up a computer model like this, and the whale, so this bit is the spiral net, and this is the sound going in, and you can see it is trapped. And you form this wall of sound, but whatever you do, no matter what angle you start at, you always produce a quiet area here. And that happens to be the region where the whales come up. It's my MO again. Compelling story. Who's going to swim through there with a microphone and disprove me? But it makes sense. It all hangs together. And so if you look at the latest BBC documentaries, they now include the sound. as a key element to the net, and it's on the whale watching tours. It's in the pattern. There's a few university groups now looking at it. So that made sense to me. What really didn't make sense to me was when I saw this video from a BBC, which showed dolphins also releasing bubbles to hunt.
They're being released by the dolphins, working together in teams. They use the bubbles to corral the sardines into ever tighter groups.
That made absolutely no sense to me. Because the dolphins, when they're doing this, they're not using their sound to make whaley calls. What they're doing is making a sound like this. It's sending out a series of clicks because it wants to hunt and echolocate the fish. So let's say the fish is the gentleman there in the green top. What I would do is click, and from the two-way travel time for the click to come back, I'd know my distance to him. And so I found my fish. But bubbles are extremely powerful acoustic entities, and they will scatter far more. So if I'm a dolphin and I've made bubbles, there's no way I'm going to detect him, because the rest of you will be reflecting the click back at me. It's what we call a clutter problem. You're faced with a load of targets that aren't your real target. They're just scattering in the way and making much more. You know, like we used to drop tin foil in front of radar, that kind of thing. So why would the dolphin blind its best sensor, its echolocation, right at the time when it needs it most? And that's what struck me the moment I saw that. What's this dolphin thinking of? Now, I know what you'll say. You'll say, but dolphins have great sonar. They don't. Dolphins have a mediocre sonar. If you put a dolphin on a table next to the best man-made sonar, the dolphin is mediocre in terms of power, frequency range, everything else. It's mediocre. But what the dolphin has is fantastic capability. And that's because of, I think, two things. One, the dolphin is a mobile platform. It can look at a target from many different directions, and it's got a brain that's been trying to figure this out for 20 million years. I can show you this is the kind of scattering for underwater signals, underwater targets that we're used to seeing. This is, however, what happens when you put the best man-made sonar in a tank of water, and somewhere here, within 2 meters of the sonar, there's a big steel weightlifter's weight like that. Should be easy to find, except we've made bubbles, and you can see the weightlifter's weight is lost. But now we don't, I'd like to figure out how the dolphin does this, but we don't do, in the UK, we definitely ethically don't do experiments on dolphins. So all I do is sit and think. There's no option but to think. So I thought, what signal would I design if I was a dolphin, 20 million years to think about it? And I came up with this signal. The dolphin sends out a click, click, and I'm going to give it amplitude 1. And shortly after, it sends out an identical click, but with half the amplitude. Or another fraction. Could be a third, could be 2/3, so long as the dolphin knows what the amplitude fraction change was. And then what happens? Well, providing the dolphin can subtract its memories and do quadratic maths, this works. Here we go. This is what happens. I'm calling this thing psi, this signal, and the echo from the fish is psi. This gentleman is just a lump of fish meat, and I send it out. But the bubble, when you hit it, it expands and contracts like that. It's quite active, and so its echo is psi squared. So what happens? Let's say the dolphin sends out click, click, and gets back this whole load of click, clicks. And it can't see the fish for the bubbles. But then, mentally, it starts doing things. It calculates twice the second echo plus the first echo. So that's the second echo, that's the first. So that's 2 times a half, the second echo, plus 1. It's 1 plus 1 plus 2. Gets a strong scatter from the fish. But what happens with the bubbles? It's 2 times a half squared plus 1 squared, which is 1.5 squared. Also strong scatter from the bubbles. But now it takes that first echo, its memory of that first echo, and subtracts from it twice its memory of the second echo. So from the bubbles, it gets half squared minus 2, sorry, 1 squared minus 2 times a half squared, 1 and 2 half there, and that gives a half, so it's a weak echo from the bubbles, and from the fish it gets nothing at all. 1 minus 2 times a half is 1 minus 1 is 0. Fish becomes invisible. You see, fish has gone invisible, so now we can't see him at all. But if we flick between those two memories, a fish that goes invisible, as you flick between memories, flashes, and you find your target. So I thought, that's what I think dolphins are doing. Can't prove it. It sounds less compelling than the Titan stuff. But I can teach a computer to do this, and when I do, there it is. Now it's getting more compelling. As soon as I tell a computer to do this, it finds the weightlifter's weight. This is exactly the same data. It's not taken on a different day. It's exactly the same signals. Find the weightlifter's weight. Now, this was important. Leave dolphins for a minute. I've made a man-made sonar. Why is a man-made sonar important? We'll get onto that second. Oh, and if you listen to the dolphin click again, they're not clicking at the same amplitude. They kind of vary, loud, soft, loud, soft. They might just be being lazy. They might be quirky. But they might be doing this. Who knows? We'll never know what the dolphin's really thinking. But we have a man-made sonar. We published it here. Nice paper. Do dolphins benefit from nonlinear maths when processing their sonar returns? and somebody published it. But now I've got a man-made sonar that works, and that matters because it's 2012, and I was worried about all these kids because these kids are living around the Persian Gulf. And the Persian Gulf is filthy with mines and explosives from the previous 2 decades of war. And you can see the problem. If you look around the coast here, it's full of bubbles and mud. Come down from the Tigris and Euphrates and waves breaking, and you can't see mines. And mines are a big problem. Obviously, during warfare, you don't even have to have more than a couple of mines. You stop operations the moment a mine goes off. And the Americans sent out divers to find the mines, and all they could do is feel with their fingers. They couldn't see a darn thing. They sent out dolphins. The dolphins all died from infection. And the beach is terrible, but people were trying to live a life again. So I thought, let's make a man-made... We've got a sonar now that can... The only sonar in the world that can find these mines. And it's a very valuable piece of kit. It's out there in production. A mine, you can buy a mine for $1,500 quite easily. And it can obviously cause millions worth of damage and tragedy. But when it did this, I knew that the maths I'd fed the computer didn't care that this was sound. It could be any radiation. We could be fixing up an MRI to try and send out 2 pulses for each one and instead distinguish tumorous tissue from normal tissue. Or, thinking about these poor kids again, we could be building a radar. Because I'm thinking about this bloke. This bloke is a worker trying to clear up mines and things after war in Iraq. And people who make improvised explosive devices try to get rid of as much metal as possible so that it's hard to find. But the last bit of metal, the one they can't get rid of is the trigger. It's about I should have brought one. I had one in my pocket earlier. It's about 2 centimeters long, 2 grams. Can't get rid of that, but it's a tiny piece. So I thought, but if I equip a radar, can it find that? So we took that trigger, we took a load of junk, metal store, we took a number of mobile phones, and we took a huge metal plate, and we buried them. Well, they were buried, and we didn't know where they were. Now, they each show up on the radar that I've designed, and this is logarithmic scale. So this thing is red, which means that it's 30 decibels stronger than anything in blue. 30 decibels is 1,000 times in power. So this thing in red scatters 1,000 times more powerfully than anything else. And you want to know what it is, because the problem this person's got is not just finding this small bomb trigger, is the bomb trigger is buried with Coke cans and cavity ties and bicycles, and it's a clutter problem. I'm trying to make sure that that thing can be found amongst clutter. So when we bury them up, yep, it's the bomb trigger. And we can tune it to find mobile phones, which is useful, because if this building collapses, radar won't find you. You're just bags of water. But you're mostly holding mobile phones. So this can find the mobile phone, and it doesn't matter if the mobile phone's batteries are taken out or it's been run over by a car, it still finds it. So it's a way of finding people in catastrophe zones. Good. Now, published it again, radar clutter discrimination with twin inverted pulses. That was a nice paper. Right, now we've been looking at this bubble, which was the bubble that the dolphin was dealing with, and I'm going to change it around a bit to this bubble. You change the sound signal that you shoot at a bubble, you can change the kind of wobble it does. And I wanted to clean. So this is a microscopic cleaning bubble, microscopic scrubbing machine, if you like. And it has these ripples, and if it'll go near any dirt, it'll shimmer them off, scrub them off. So I built it into this device, and what happens is electricity and water in separate cables, obviously, go up into this kind of horn shape, and the electricity makes sound, and the water comes out, a very gentle stream of water, about 1 litre a minute. And you turn on the sound, it cleans. Here's an example. You've got a contaminated hand, and no sound on at the moment. Turn the sound on, cleans it off. It's quite nice. And how does it work? Well, this is a kind of schematic. Water goes up this pipe here, fills the cone, comes out a little nozzle at the end. Sound waves are generated from the back, and they and little bubbles travel down the stream to the target to be cleaned. And clean it like that. And it seemed very nice. Now, that bubble isn't just swiggling like that. It's not rising under buoyancy. And that's because I can use sound and the way it reflects off things to control where the bubble goes automatically. And I can use a sound field that makes the bubble find the things I want it to find, particularly cleaning crevices. It's really easy to clean. This is flat floorboard. Really easy to clean this. Wipe it, mop it, scrub it. Very hard to clean in the crevices. So I want to use the sound to program the bubble to find crevices and clean in them. And that's shown here with a piece of glass. And in the glass, I've got something the thickness of a human hair. That's that cavity there. It's a little a pore. And on the top, I've got a sticky contaminant. And the sticky contaminant fills this little pore. But it doesn't look black there because you're only looking through the thickness of a human hair. At the base of it, I've built a cleanliness sensor here that'll tell me, and this is the output here, whether it's dirty or clean. And it's saying the base of the pore is dirty. And as I run the video, the line will move across it as before. So let's see what happens. Right, the water hits the gunk at the top, washes it away. Now the bubbles have found that little crevice, and when they wiggle to the bottom, the sensor goes clean. It's really good at cleaning stuff. I'll do it again. If you look carefully, you might just see the edge of the bubbles ribbling away as they eat through the dirt. So it's good at cleaning. Now, another apocalypse I'm going to talk about now. Obviously, this can clean all sorts of things, and everybody, whenever I show this, people come up to me with things they suggest it can clean, honestly. But here's an example. The nice thing is it's a very gentle cleaner, doesn't damage. And by 2050, if we don't fix things, we'll have a hunger apocalypse leading to migration and war. So by 2050, there'll be an extra 2 billion people to filled, and extending food shelf life is critical. Currently, 25% of the world's food calories and 50% of the weight of food is wasted before consumption. It's allowed to rot. Salads are crucial because they're nutritious and they don't have the environmental impact of trying to produce meat. But we need a gentle cleaner because damaged salads, they rot more quickly. So this is some ready-to-eat salad from a supermarket bag. So I've taken it out of the supermarket bag, run it under a tap of water for 1 minute in your kitchen. And these little blue dots are E. coli from animal feces. So they're still on there after 1 minute of washing of a ready-to-eat salad. And if you clean for 1 minute with my ultrasonic stream, they're gone. So it'll clean it. Does it extend? Some graphs, but honestly, go to the papers where we make our graphs like this logarithmic so you can see things. So this is the ready-eat salad. This is the bacterial count on it, and this is 6 days later. This is if it's washed in the ultrasonic stream, and 6 days later. Right, how does it affect shelf life? Well, this is some basil, ready to eat, left for 7 days. And this is ours. Obviously, it looks better. If ever you leave your lettuce or salad in the fridge, you go slimy. That's bacteria. It's a bacteria, a carpet of bacteria called biofilm. It's slimes all over your salad. That's what slime is on salad. Right, how is this useful? Well, leads to illness. 1 person dead from E. coli and 120 hospitalised. It's about 2 deaths a year per country from eating salad that's got E. coli on. Deadly E. coli outbreaks hits 15 states, but the FDA chose not to publicise it. So we published this. Again, if you're interested in this, you can grab this paper. We should have a follow-up coming out soon. Credit again to my co-authors. Oh, right. So we can clean salads and we can clean everything you're thinking of. But you can't build a business. I want to build a business. You can't build a business cleaning salads. Because when you build a business and it's a disruptive technology, you've got to focus on one thing. And there's got to be one thing that nothing else can clean. Absolutely nothing else can do this. So I decided on venous leg ulcers, which I'm going to talk about. It's the last topic I'm going to cover. Venous leg ulcers, content warning, I'm about to show you one. If you're squeamish, close your eyes and I'll tell you when it's okay to open it. Here comes a venous leg ulcer. So they're pretty brutal things and they're very common. It's off screen now, so those who didn't like it. So they cost the UK NHS $2 billion annually. Other types of chronic wounds add another $8 billion annually to that. Venous leg ulcers have less than a 45% healing rate. We've found them lasting for 17 years or more. Patients say things like, there was so much fluid coming out of my foot, it smelled really bad like meat juice and it seeped through everything. They talk about the tremendous pain they're in, and what here is a medical condition leads to social isolation. People get stuck, and then it becomes a social cost as well as a healthcare cost. So we thought, can we heal these? Because they're infected but with bacteria, but the bacteria aren't like many of the older generation were taught bacteria in school. It's kind of little bag of gel with a tail that wiggles around, swims around. That's not the way these bacteria, they form something called this, a biofilm. This is a slimy thing on lettuce. You have lots of different bacteria and fungi grabbing hold of bits of particles and cloth and anything else, all living in a community that changes over time, because one bacteria might produce a bit of acid that the other then eats up. And they protect each other, so they become very resistant to antibiotics. So we want to clean that. So when you've got a venous leg ulcer, it's really like your body's like a car. It's got 2 things wrong with it. The exhaust pipes had dirt shoved in it, and the battery's flat. The exhaust pipe is the bacterial biofilm, the dirt, and the battery being flat is your body just gives up, and the cells that should heal just say, stopping. And so these wounds last for years. So how can we treat it? Well, every venous leg ulcer, VLU, gets washed in saline clinic in the UK about twice a week. Take the dressings off, it hurts, they pour saline on, they dress it back up. Twice a week. So I thought, well, can we clean the biofilm off with this device? So you keep the clinic visits the same, but replace the ordinary saline wash with a saline wash through Law's liquid acoustic wound stream. That's this device here. So do a bit of maths, get it all done, sorted, bish, bash, wash. So first of all, obviously you're not allowed to do experiments on humans till you can prove you're safe and efficacious. So we worked with pig skin. This is washing dead pig skin that's been infected with Pseudomonas, a superbug, for 1 minute. And if you wash with ours, it's much cleaner. Go to the paper for graphs. Oh, here's some graphs. That's the control, wash with saline, and again, nothing, very little from Law's device. So here, the acoustic bubbles cleaning would lead to healing if the pig skin wasn't already dead, but it can't heal because it's dead. So that's cleaning out the tailpipe of the car. But you've also got to fix the second problem, which is the battery is flat. And I'm afraid for that, you need magic. So, dial up the magic. Bring a lot more maths in. We say, can we actually bring magic? Because what I want to do is take those cells that have given up and wake them up. And tell them to start healing again. Say, look, for years you've been living there doing nothing. I want this skin to heal. Now, to test whether you're doing that separate from cleaning, you make a wound and you keep it clean. No bacteria there. So there's no cleaning effect. This can only be due to the waking up the cells. So this is 7 days after 2 minutes saline, or Law's wash on a lab-grown skin. This is the sideways look through the skin, and I have to credit my head of biology, Tom Secker, for all these slides. He does a wonderful job with his team. So this is your skin. This is the outer layer, the stratus corneum. It's dry. It's kept you safe from infection, mostly for about 100,000 years. You should be very grateful to this skin. The epidermis here, the dermis, and it's full of little cells here that have given up on healing. So we strip away the top of the skin and we keep it alive for 7 days. And this is the control. You can see this bit of tongue skin has grown back here, and here it's not even tried. Now we wash it in saline for 2 minutes, and then leave it for 7 days. Little bit of skin growth. Now we wash it in our device. There's quite a lot of skin growth. We're waking up the cells. Now, let's keep going, because this was the early results with lab-grown skin before we had much money really, before we were allowed to move on. So, this skin was never infected. This living skin was never infected, and the acoustic bubble still stimulates it to heal. So, cell response. What's happening to the cells? Here, using a green colour, we've stained keratinocytes. So these are, this is a kind of tough cell type that covers wounds at the start. So this is washing with saline for 2 minutes and leaving it for 7 days. And this is with washing with the Law's device. And we can see the keratinocytes have really woken up and done their job. This is fibroblasts. Fibroblasts live down here. They stain more bluey, and they work their way, and they fill in the gaps made by the hole. And here they are waking up. Again, this is from a 2-minute treatment. They're shown with this dappy stain. We published this. Again, credit to my co-authors. But if you're going to make a treatment, 2 minutes is quite a long treatment. So can we get it down to 5 seconds? Bit of maths, and here we go. So this is uninfected harvested skin. So this is skin given up voluntarily by a 66-year-old female with quite a deep wound in it, and it's uninfected. And you can see this control. There's a deep wound here. That's again the epidermis, and here you've got a deep wound and lots of holes in the collagen and elastin here. So 2 examples, untreated, 5 days after wounding. Here is 5 days after wounding when you've had 5 seconds of saline treatment, and then that's what happens if you treat for 5 seconds of Law's and wait 5 days. So you've healed this up, and all this is starting to look much more healthy. This collagen and elastin and such like. So now we take the infected human skin and we infect it with MRSA, which is a superbug. And the skin is harvested after the 5-second treatment. And this is with saline only and no bubbles. And if you see any little purple dots, that's the MRSA. So here you are, you see absolute hordes of it, and they penetrate quite deeply into this, into the flesh structure of collagen and elastin here. Some there, really burrowing deep into any crevices like this. And right here at the edge of the wound where you've got this kind of undermining, really horribly infected there. Now, and that's been washed in saline. Now we take the same infected skin, infected with MRSA, and after 5 seconds of washing with the Law's treatment, remember how the undermining is a crevice that we can seek out all these crevices and heal and clean them out. No, they're all clean. These bits, these large blobs of purple are nuclei from human cells, probably fibroblasts. And they're all clean. We've cleaned it all out, even these things. So, healing with just saline and sound, no antibiotics. We're not using any drugs. It really is air, sound, and water with some salt in. So what's the value of therapy that heals using sound and water and no antimicrobials, antibiotics, antivirals, antifungals? Well, unless a solution is found by 2050, antimicrobial resistance will cost the global economy more than the current than the current world economy, and be killing more people than cancer. And that's because we might be, I might get a cut, be infected by you're all bacteria out in the fields, out in the sewage. I might get a cut and be infected by one of you. I get an antibiotic, I'm better. But then I urinate the antibiotic out, and it reaches the fields, and those of you who are bacteria who are susceptible to it, you die off, leaving lots of niches, empty seats for the ones who are resistant. So next time I get cut, I can't treat it with antibiotics. It's one form of antibiotic resistance. You can see a problem here. This is the prevalence of a strain of antibiotic resistance in various countries. In 2009, 2016, it's spreading. One reason is we fly in planes. Planes are big metal tubes where we put toilets next to the food preparation area. Nobody knows how anybody washes their hands. And the moment you get off, you touch this rubber strip. So bacteria can live on that rubber strip for a year. So I can touch it, and then someone from Brazil can touch it with completely different bacteria, and those bacteria can start communicating, swapping DNA, another form of antibiotic resistance. So imagine how bad 2050 will be if today the cost of unhealed wounds, half of it, 2 billion a year, is venous leg ulcers. And these are the others waiting to happen. This orange one is diabetic foot ulcers, for which we amputate 6,000 feet a year in the UK. So I basically want to tackle all of these, but I'll start with VLUs because they make the statistics make sense. The leading cost currently to the US is cancer, diabetes, and the third most costly thing, if you factor in things like nurse time as well as drugs, is chronic wounds. What will it be like in 2050? Well, I've been to rural, this is northern Ghana, where the number one cause of death is infection currently. And I took my device out to see if people could catch on how to use it. They caught on very quickly, so I think it's got potential to go out there. Anyway, final slide. So the last topic we've done is healing just using air, sound and water. We've looked at skin healing with air, sound and water, and we need it because the NHS spends 2 billion a year, 45% healing rate, 17-year persistence, and meat juice. In April, next month, we start treating patients. So this is my company, jolly bunch of people. And this is me in Magdalene, listening to bubbles. So thank you, Magdalene, where I started listening to bubbles. Thank you very much. Absolutely.
Professor Leighton is very happy to take some questions, and I will. We have a microphone, a roving microphone, 2 roving microphones. Do please make use of them. Who would like to ask the first question? Professor Clary.
Thanks, Tim. That was great. Just to go back to your observations with on the planets and the moons.
Yes.
I mean, there must be other techniques that are complementary to what you're doing, particularly spectroscopic techniques of the molecules that are involved. Do you interact with those sorts of observations?
There are certainly, and spectroscopic techniques have been used for a long time. It's a peculiar field to break into. If you're sending a probe, the number one, then there's a big priority of what goes on a probe, and it's a brutal world in that missions get cut all the time, And these are long-term missions, so people can plan for a mission 2038 and have it killed halfway through. And so they're very careful about prioritizing. And so tried and trusted technologies are the way to go with these things, because you want something, you really don't want to be messing around. So I am the tiniest grain of sand in the space exploration thing of anyone. And you'll find that the space missions must prioritize tried and trusted technologies. And you're very, very lucky if you get something wacky and experimental put in there. And in fact, on this mission, we couldn't get the microphone. I say we, I've got to credit the teams in France that did the heavy lifting in getting over and getting this done, and other countries. We couldn't get the microphone there to listen to lasers cracking to measure the temperature. The microphone was there because you could hear whether the pumps were working with it. That was the purpose of the microphone. And with that justification, the microphone got on the mission. Once we got a microphone there, we could use it for all sorts of other stuff. You see what I mean? We're high risk, low priority when it comes to missions. It takes a long, long time for something new to come into regular use on a space exploration. But in terms of can we use in collaboration, when those people are getting all their data in terms of chemistry, absolutely, because we'd used that data already to predict how sound would be absorbing on Mars. Interestingly, C.S. Lewis wrote a book about Mars called Out of the Silent Planet. And the silent planet was Earth, because the people on Mars could sense spirituality, and we had none. But Mars has so much carbon dioxide absorbs the atmosphere, so we thought Mars would be almost silent. Sound won't travel to distance. And in fact, we're still sitting there thinking, how the hell did we hear that helicopter at 100 meters? So we use certainly all the information we have about the chemistry of the atmosphere to make predictions about how the absorption should be for a stationary atmosphere, which then allows us to look at the differences that tell us about the turbulence and such like that's happening. Right.
Thanks, that's marvellous. One of the major loss of man-hours in the NHS is due to dermatitis caused by repeated cleaning of hands, particularly using alcoholic-based hand-cleaning agents. Do you think your device would have a role in places, particularly in places like theatre and ITU, where multiple times a day people need to be cleaning their hands?
Yes, my team and I built and patented a faucet tap under which you can clean your hands using the ultrasound. So the patent's out there. But as a business, again, it's going to be something down the road. It's not the first thing, purely because of all the... You would have to, and we put this two ways. One, you have to get it accepted. Trying to get something accepted in the NHS is really hard if it's physical. You say, I'd like to plug this into your water. They say, no, you won't. Or they'll say, well, I'm interested in it. Give me a full day of your time, and then I'll tell you I'm not the person with the authority. They don't like you plugging things into their infrastructure. And the second thing is, if you're going to do something like a faucet, you have to spend probably an extra 20 million before you can make a sale, because you can't advertise something and run out on day one. You have to build a lot of product, have warehouses full of it, ready to ship, because your company loses credibility if you run out. So you've got to be building stuff for years, building up, and then please buy and people sell. We can't afford to do that, which is why we've got out for a high value, small volume product, which is the wound things. But certainly hand cleaners we can do. It's just we have to have a market that we can meet in order to justify paying all the salaries. Because it is, for each product, it's about 20 million, I think, you've got to spend before you recoup any money.
Shall I come? Thank you. Truly fascinating talk. There's so much you can do about air bubbles. You said, I'm going back to your dolphin concept. Yes. of fishing. And of course, trying to prove that. Not actually to prove it, but could you actually consider using that kind of concept as opposed to a more kind of refined way of actually fishing without using big nets or subtle ways of catching fish?
For catching fish?
Yes, or in terms of kind of big trawlers trawling the sea. Is there a way of using that for a more subtle way of less damaging way of fishing?
It's a good thought. I mean, they do use fish finders like that, to detect where they are.
Yes.
I think we've got to be very careful where we put sound in the sea into the sea to alter behaviour, because it's a pollutant. Sound is a pollutant. I mean, if you look at outside of Boston, for example, you can see as you map and listen, you can see all the whales, and then a ship comes through. Whales can't hear each other. We can't hear them. Nothing can. We have done it on a small scale. There wasn't time to put the various things in. I worked with environmental scientists and environmental engineers. They're really lovely people to work through. And the problem they had is that chemical factories and power stations, they need a lot of cooling water. So they suck it out of streams and streams and rivers. And they suck fish up as well at the same time and kill a lot of fish. And a lot of fish go through dams. You can get, I think, 8 ton of fish killed a second when a big dam starts sucking fish up. And in the UK, so you think you might put grill against it. And grills are okay against strong, swimming, fast fish. In the UK, we have eels. Eels are protected species. They're endangered. And they're weak swimmers. They get sucked through the grill. So what we decided was to build an acoustic scarecrow. And this has been deployed now. And we built underwater mazes, and you can steer the fish through it we're using sound. So you can put the right sounds around these extraction points, and the fish stay away from it, and they never get caught in the high flow near the extraction. So we've done that, and that's because we're affecting a localized piece of a river, really. But I'm very cautious about putting large amounts of sound into the ocean.
Just about your wound machine, I understand how you've cleared the blocked exhaust, but I'm not sure, why does it work, why do you think it works increasing the fibroblast healing? Because that, you said it was magic, and it's not clear to me what the mechanism is here.
No, you've hit the nail on the head. And again, I'm a commercial entity, so I'm limited in what I can say.
Give me a theory. Give me a.
I can give you an idea. I mean, and it's, I'm not exaggerating. There were no small medical device companies bringing anything disruptive. They get destroyed in this country. We've had people turn up at the door, pretending to be fire officers, pretending to be landlord agents, just wanted to photograph everything. I've been in lifts with heavies from big companies. They don't want this stuff, and they want the rights to it so it can never be built. That's the thing. So I'll tell you what I'll tell you what it is. A lot of these cells respond to mechanical stress in some way, and I think they have ceased communicating to each other. So we know these cells communicate to each other. They send off MM9 and such like to each other in a programmed sequence, and that all that sequence is stopped. And I think what's happening is the sound wave is coming down. It contains shear, it contains stress, and it's the right signal to wake these cells up and give them a little massage, if you like. And then all he has to do is start triggering one of those MMP signaling rotors and kickstart the whole thing again. That's all it has to do, and that's what the sound does. So it's close to magic, but it is science.
If I may.
Yes, please.
Thank you.
Last question, I think.
Thanks very much. So my question is, as a researcher, how do you go about making a difference in society? And the reason behind it is, if we look at your venous leg ulcers, it doesn't appear, at least to me, as though the intuitive route to making a difference there is to start by putting probes in bubbles. And so I just wondered if you might share how researchers could go about making a difference.
It's a very good point. I think we have to be problem solvers and not solution sellers. So we mustn't say, the thing I'm good at is what I did my PhD at. It could be of use to, and then trying to push that solution on to the world. You've got to look at the world and say, what is the problem here? And if I can think of a solution, what's a solution that is viable? You know, Africa is full of technologies that we've given them that don't work because they need electricity supply that doesn't stop every 4 hours, that kind of thing. So you have to find something that you have to be a problem solver and come up with a solution to that problem that you can that the people can implement. Don't get trapped into thinking your expertise is what the world needs. It isn't necessarily. It may have a use. Publishing a paper is almost no use. It's there to give you, at some point in your journey in trying to make an impact, someone say, are you a fraud? Well, if you've got a ton of papers, it backs you up. The regulators like it, that kind of thing. But of itself, it's not enough. And I think publishing a paper is a bit like throwing a ball to someone and saying, you catch it, it's your problem. And I think you've got to be holding the hand of the person who you think really could use this and help them catch that ball. And it's not just them. Who actually makes the difference? Who moves the needle? So it might be procurement. It might be legislator. There might be a whole train of people who you want. So getting some of the NHS, you need doctors to be excited, but you have to get procurement in the right, you have to on side. You know, you have to get facilities on side. You have to build a solution that they will have. So I think that is key, I think, is to be problem solvers, not solution sellers, and then really work hard to identify who it is who needs to have their hearts and minds changed to implement that solution in the real world. Right? That's crucial.
I think at that point we must stop and let Professor Leighton have a drink, which is going to be vitally important. Tim, when I first knew you, when you were a research fellow, I was immensely impressed by the enthusiasm you always showed for work on bubbles. I can't pretend I understood a word of it, but this evening I've at last seen how it all comes together, from sound on Mars, through the quadratic mathematical skills of dolphins, to a revolutionary treatment for wounds, and perhaps the bit that resonates so well with many of us, how to get your revenge on your PhD student. You're not allowed to experiment on humans, but clearly you are allowed to experiment on your PhD students too. But your enthusiasm, the way in which you have developed solutions to problems rather than going out and setting out with a solution that the world just needed, whether it knew it or not, came through brilliantly, even to a non-scientist like myself. And I think we've all had a real treat of a lecture as a result. So will you join me in thanking Tim very much indeed?
Thank you very much. Thank you, Master. Thank you. Thank you.